Theorem show that LP space is a reflective. Proof. First, we prove that if 1 is less than p is less than infinity and q is a conjugate to p, then LP star equals to LQ. Let x equals to xi1, xi2 and so on, xn, so on be a generic elements from LP so that sigma n varying from 1 to infinity modulus xi n raised to power p is less than infinity. Equation 1. Now consider the sequence of elements from LP. E1 equals to 1, 0, 0, so on, 0 and so on. E2 equals to 1, 0, 1, 0, so on, 0, so on. E3 equals to 0, 0, 1, so on, 0 and so on. Since x minus sigma k varying from 1 to n xi k ek equals to 0, 0, so on, xi n plus 1, xi n plus 2 and so on. We see that modulus x minus sigma k varies from 1 to n xi k ek equals to sigma k varying from n plus 1 to infinity modulus xi k whole raised to power p, xi k raised to power p whole raised to power 1 upon p tends to 0 as n tend to infinity. Since it is a remainder of after n term of the convergent series equation 1, it follows that x equals to sigma k varying from 1 to infinity xi k ek. Let f belongs to LP star and let s n equals to sigma k varying from 1 to n xi k ek. Since f is a linear, so fsn equals to sigma k varying from 1 to n xi k f of e k. Since Sn tends to x and f must be a continuous, being a bounded linear transformation, we have fsn tends to f of x. Therefore, f of x equals to sigma k varying from 1 to infinity xi k f of ek. To prove the theorem, it is sufficient to establish the following contention: letting alpha k equals to f of ek, k equals to 1, 2 and so on, where f belongs to LP star, where p is greater than 1 and 1 upon p plus 1 upon q equals to 1. The mapping of T transformation from LP star to LQ is defined by T of f equals to alpha 1, alpha 2 and so on, alpha and so on, constitute a convergence between the LP star and LQ. We first show that the mapping does indeed take LP star and LQ. Consider the vector x equals to beta 1, beta 2 and so on, beta n, so on, 0, 0, so on from LP. Where beta k equals to modulus of alpha k raised to power q minus 1 sgn alpha bar k, where 1 is less than equal to k is less than equal to n, sgn equals to signum function and 0 is n equals to 0 when n is greater than k, and alpha is the statement of the contention for 1 is less than equal to k is less than equal to n. Modulus beta k equals to modulus alpha k raised to power q minus 1. Now since 1 upon p plus 1 upon q equals to 1, so p into p minus 1 equals to q, and we have modulus beta k raised to power p equals to modulus alpha k raised to power p into p minus 1 equals to modulus alpha k raised to power q. Thus alpha k and beta k equals to alpha k modulus alpha k raised to power q minus 1 equals to modulus alpha k raised to power q equals to modulus beta k raised to power p, equation 2, which implies that norms of x equals to sigma k varying from 1 to n modulus beta k raised to power p whole raised to power 1 upon p equals to sigma k varying from 1 to n modulus alpha k raised to power q whole raised to power 1 upon p, equation 3. Now since we can write x equals to sigma k varying from 1 to n beta k ek, it follows that f of x equals to k varying from 1 sigma k varying from 1 to n beta k f of ek equals to sigma k varying from 1 to n alpha k beta k by the hypothesis equals to sigma k varying from 1 to n modulus alpha k raised to power q by 2, equation 4. But for every x belongs to LP, we have modulus f of x is less than equal to norms of f and into norms of x, which by equation 3 and equation 4 gives modulus f of x equals to sigma k varying from 1 to n alpha k raised to modulus alpha k raised to power q is less than equal to norms of f into norms of x is less than equal to norms of f into sigma k varying from 1 to n modulus alpha k raised to power q whole raised to power 1 upon p. Dividing the throughout by the last term on the right, we get sigma k varying from 1 to n modulus alpha k raised to power q whole raised to power 1 upon p is less than equal to norms of f, equation 5. This shows that the sequence of the partial sums Sn equals to sigma k varying from 1 to n modulus alpha k raised to power q whole raised to power 1 upon p is bounded and monotone increasing, which therefore converges. Hence the image of the f under t, the sequence alpha k, is a member of LQ. We shall now show that T is a isometry, or that norms of T of f equals to norms of f. Equating 5 implies that sigma k varying from 1 to infinity alpha k raised to power q whole raised to power 1 upon p equals to norms of T of f is less than equal to norms of f. Therefore T will be a isometry if we can prove that norms of f is less than equal to norms of TF. Let x belongs to LP, and writing x equals to sigma k varying from 1 to xi k ek. Hence f of x equals to sigma k varying from 1 to infinity xi k f of ek equals to sigma varying k varying from 1 to infinity xi k alpha k. And by the triangle and the Holder inequalities, modulus f of x equals to sigma k varying from 1 to infinity modulus psi k into modulus alpha k, which is less than equal to sigma k varying from 1 to infinity modulus alpha k raised to power q whole raised to power 1 upon q into sigma k varying from 1 to infinity modulus psi k raised to power p whole raised to power 1 upon p. But since sigma k varying from 1 to infinity modulus psi k raised to power p 1 upon p is just as the norms x, therefore the last inequality becomes modulus f of x is less than equal to sigma k varies from 1 to infinity modulus alpha k raised to power q whole raised to power 1 upon q into norms of x for all x, which implies that norms of f is less than equal to sigma k varying from 1 to infinity modulus alpha k raised to power q whole raised to power 1 upon q equals to norms of t f. Therefore norms of t f equals to norms of f, and hence t is a isometry. Being isometry, t is 1 to 1. To complete the proof, it is only remains to show that t is onto LQ. Therefore, to every point beta k of LQ, we must find a linear functional g belongs to LP star that maps into beta k, that is tg equals to beta k. Consider x equals to LP. We write x equals to sigma k varying from 1 to infinity psi k ek, equation 6. We now claim that the required functional is given by g of x equals to sigma k varying from 1 to infinity psi k bk. To verify, this is equation 6. To verify this, we first note that the representation of equation 6 is unique and therefore g is well defined. Clearly g is linear on LP. Furthermore, modulus g of x is less than equal to sigma k varying from 1 to infinity bk beta k psi k equals to sigma k varying from 1 to infinity modulus psi k raised to power p whole raised to power 1 upon p into sigma k varying from 1 to infinity modulus beta k raised to power q whole raised to power 1 upon q equals to norms of x into sigma k varying from 1 to infinity beta k modulus beta k raised to power q and whole raised to power 1 upon q implies that g is bounded. Also, g of ek equals to beta k for any k, and therefore t of g equals to alpha k and equals to g of ek equals to beta k. So t is on to mapping, hence LP star is a isometrically isomorphic to LQ. So we have LP star equals to LQ, therefore LP star star equals to LQ star equals to LQ, because LQ star equals to LP, hence P is reflective.